Okay, good morning, everyone. Okay, so we finished the chapter 10, uh, including the parametric equations and the polar curves. What I would like to do today is continue, uh, maybe a little bit preview exercise for one or two questions. And after that, we're going to move to chapter 11. Chapter 11, maybe introduction for chapter 11. Okay, from your exercise, is there any question? I have put the answer on the Moodle. You can check on the weekly schedule on the Moodle. Okay. Maybe I would like to make some emphasis on your exercise. Let me check my exercise. This one. Okay. So the exercise, okay. On the polar curves, we have find the area. The first one, find the shaded area, and then find the area of the. It can be intersection. It can be depends on the function. Like for example, number 2, find the area of the region that lies inside both curves. So we have two polar curves, and then it says all the area inside both of these two. Or there will be another type of questions, maybe inside the first one, but maybe outside the second one. It depends on the question. And it requires you to at least draw the curve if you're not sure the intersections. And then another type of questions, if you have like a curve that has a loop, maybe it's asking the intersection also for that loop. Is inside the larger loop, outside the smaller loop, or maybe it's just asking the smaller loop. It can be that type of question. And then exact length, for example, this part in picture. Okay. It can be the red or the blue one. And then number 5, the tangent line. I think that is the a typical question. And remember, when you are solve the tangent line, polar and parametric, they are the same. The difference is if you want to take the polar, change all to r theta, and then you can use that, or you can take back to the parametric one. I think that's simply the same. And the answer is also the same. Okay, so you could approach using just a normal parametric, or you could take the polar. And then another typical questions will be finding the horizontal tangent and the vertical tangent. Okay, horizontal, vertical. Okay, I would like to emphasize the last one here, because if you are not really careful, and if you read my answer here, okay, as usual, first we define the tangent. Okay, we define the tangent. Okay, we define by dy dx. Okay, and then we have these two components of dy d theta and dx d theta, right? And then from the definition of horizontal and vertical, we get the horizontal tangent is when it is 0, which means the dy d theta should be 0 and the dx d theta is not 0. And we got some formulation here, and then finally finds the theta, okay, when we equal it to 0, okay, for the horizontal. And then we have some theta, and this is not yet theta for horizontal. We need to check again later. So we got all the potential theta. And do the same thing with the vertical. Same thing with vertical, and we take the definition for vertical tangent, dy dx is undefined. Okay, remember, the tangent is going to be vertical, right? Which means that it's actually infinite, right? So undefined, so we take the dy d theta is not zero, and dx d theta is zero, so it's defined, something defined by zero, which is infinite, okay? And take the approach and make the dx d theta equal zero, and we take the zero, okay? And some identifications, and then we get the theta 0 and pi. And if we look from what we have here, they are the same theta, pi. But which one? Is pi is vertical or horizontal? Okay, so if you just answer this in a question, it's not fully complete. It's not fully complete. So we need to take another approach, okay, to define what is pi doing here. Is it horizontal or vertical? So how to decide which one is horizontal and which one is vertical? We need to take the limit, okay? We take the limit as theta approach pi, this dy dx or dy theta dx theta, it need to be 0. So we need to test the limit. And we need to measure the limit. So we need to actually calculate the limit. So we put all the information of dy theta here and dx theta here and use the limit. Okay. You solve with limit concept. Solve with limit concept. And it's actually equal to 0, which means that it is actually horizontal. Okay. It's actually horizontal and not vertical. So the vertical is only 0 and this angle, and the horizontal is up there. I think I write on the left side. Yeah, horizontal, that angle, and it's r theta, so the radius theta. The vertical tangent is also that one there. Okay. So that's I think one thing that I need to mention. Okay. So when you have an angle, a potential angle that has two potential to be horizontal tangent or vertical tangent, then you need to do the limit. You need to do the limit. And take the limit means you can also take the limit from the left, from the right, okay, and check whether they are the same thing. If they are not the same, which means that it's not defined, right? So probably there will be vertical tangent. Okay. I hope still remember the limit. Because I think in the next chapter 11 we are going to use limit a lot. Okay. Okay, I think that's just the I think additional point that I need to make. Okay. Okay. I think we can start with some example. Okay, some example. You can check the answer in the Moodle. Okay, you can download the PDF. Okay, I think we can try these questions. Okay. Which one you want to take? No, the first one or the second one? Is from the text. The first one, 2 sine theta and sine theta plus cosine theta. Second one is having the cardio, not cardio, it's the dimple, right? Which one you want to take? The first one or the second one? I think the first one. The first one. Yeah. Try the first one. Okay. Try the first question. So let me give you a couple minutes, maybe 3 to 5. So actually, the second one has the cosine 2 theta. So it's like a almost cardio, which actually has 2. So it's a little bit complicated if you want to draw. But the first one, I think should be not as complicated as the second one. Yeah, this is okay. This is for the projective side here. But how about this one? Maybe you can check the special value. Like 0, pi over 2, pi. Just to check how they looks like. You can imagine the sign that you learn, like this the I think also from physics, the sinusoidal, like that, right? What will happen if you have cosine? You would shift it the about 90 degree, right? So when you plus those two, what's happened? They are complement each other. So when sine is here, cosine goes down. So do you think it's a circle? Do you think it's a circle? Sine theta plus cosine theta. Yeah, you can check using the sinusoidal. Or if you would like to test when theta is 0, pi over 2, pi, 3 over 2 pi, what will be the result for the radius? Right? You can also check from that. And maybe you can add the pi over 4. Pi over 4, which is sine and cosine has the same value, square root of 2 over 2. If you plus both of them, it will be square root of 2. Okay. So this is what I mean. So when r is sine theta plus cosine theta, you can check some angles, like from 0, pi over 2, 3 over 2 pi, okay? Or, if you remember carefully, when theta is pi over 4, both of sine and cosine has the same value, right? So r will be square root of 2, right? Or let me write here. Sine pi over 4 plus cosine pi over 4. Both are square root of 2, right? So we could just write square root of 2. Now, the maximum of cosine, for example, when cosine is 0, r is 1. And when theta is 0, sine is 0. Okay. So let me start here. So when theta is 0, r is 0 plus 1, or just 1, right? And when theta is pi over 2, let me just take this to example here. Sine is 1 and cosine is 0, right? So which means, and pi over 4 is in between 0 and pi over 2, right? So if this is theta equal 0, this is theta equal pi over 2, and this is pi over 4, okay? Then if this is 1, this is 1, then this is perfectly the hypotenuse, right? Square root of 2. The length, or we could say the length for this pi over 4, like square root of 2 here. Okay. Now what will happen, and what is a possible track to connect from one here to here? Well, it's actually maybe here. That's really proportional. Let me throw a correct one. So it's actually, it goes through like a circle. And it's actually a circle. But when it's my circle, it's not good. But it's actually a circle. So the curve, let me draw again. So first we have the 2 sine theta. So 2 sine theta, remember sine, if it's positive, it's on the top. Okay, so we are going to draw on the top like this. Let me make it more proportional. Okay, let's say that is our r equal to sine theta. And this will be the sine theta plus maybe around there. Okay, maybe a little bit smaller because the one is 2 sine. Okay, it should be here. This should be exactly at the middle part of the 2 sine. The 2 sine theta has the radius maximum 2, right? Radius 2, and this one is 1. Okay. And of course, on the intersections here, it's moving maybe here. Okay, I think it should be okay. Yeah. Okay, and then the intersection here between both of the two curves. If you take a look, so this is one, this is should be a little bit to the left. Maybe draw a little bit to the left. Okay. So this will be some angle. And we are going to find that the angle is actually pi over 4. So we could take the intersections. So what we are going to find is the area here. That's the area we want to find. So first of all, we could take the intersections. Intersection, so sine or 2 sine theta equals sine theta plus cosine theta, and this is sine theta equal cosine theta, or tangent theta is equal 1. And for in between 0 and pi over 2, this is equal to, we could say the theta is pi over 4. But tangent also positive in the third quadrant, right? The third quadrant, which means it's the pi plus pi over 4, right? Or no? 3 over 4. Oh, wait, not this one. Let's see from this part first. So this is r sine theta plus cos theta. So if we define, so we have this area, the blue, this shade area. Okay. Now if we cut this, because this is a pi over 4, now if we would like to define this become 2 area, so the first one, let me draw first, the number 1 here, number 2 here. Okay. So the number 1 is the blue circle here, right? The blue circle, which means we can take the blue circle from theta equals 0, okay? Theta equals 0, which means start from here, and then it's increase until theta pi over 4. That is the first area. Okay. Okay, now the second area is the green one. The green one starts from pi over 4, increase up until here, and we need to know here is actually 3 over 4 pi. That's when 3 over 4 pi is, let me check. 3 over 4 pi is 180, 45, is pi over 2 plus pi over 4. In the second quadrant, this is 3 over 4 pi. Yeah, it's 3 over 4 pi. So here in origin, that is 3 over 4 pi. And then we could take the area is area 1 plus area 2. So area 1 is from 0 to pi over 4. Half r squared. R is 2 sine theta. So 2 sine theta. And squared d theta plus. Or if you want, maybe calculate the first area and then the second one and then plus both of them. Or you could do the directly. Okay, and then this is half plus squared d theta. Okay. Okay, and then we could make a squared this part, and we have sine squared theta plus 2 sine theta cos theta plus cosine squared. And we could write 1 plus sine 2 theta, right? And for sine squared theta, we could exchange to the double angle formula. And this is 4, or maybe let me to make it the same, because it's multiplied with 2, so it will be sine squared theta, or 2 sine squared theta, so 4 by 2. Okay, so we could directly exchange this. Oh, it's not plus, sorry, should be minus. Okay, and then we could integrate 1 minus cosine 2 theta d theta, and then plus 1 plus sine 2 theta d theta. And I think it's for the integrations as to be easy, right? Nothing, no need for some techniques, just normal integrations. So this will be theta minus sine 2 theta over 2 from 0 to pi over 4, and then plus, this is theta minus cosine 2 theta divided by.
Excuse me. What happened to 1 over 2 in second integral?
Ah, right. This is okay. okay. I forgot this, the half one. Okay. This should be half of that. Okay. So maybe let me write. This is half theta over 2, and this will be over 2, and by 2 become 4, right? Okay. Is it correct? Correct, right? Okay, now we take, this is pi over 4 minus half and all 0 plus 3 over 8 pi and 3 over 2 pi is 0, right? And minus pi over 8 minus 0, right? Or maybe, yeah, maybe just minus pi over 8. 2 over 8. 2 over 8 is pi over 4. So pi over 4 plus pi over 4 is pi over 2, right? Pi over 2 minus half. Or pi over half pi minus 1. Okay. Do you want to write from the top or this one? This okay? Any questions?
While the second part is power from to
Oh yeah. So here from this part, we know that tangent theta is equal 1. The theta should be pi over 4. If we take the other parts, it will be 5 over 4. But if we take, remember, if we take, let's say we move from pi over 4, let's say we move pi over 2. So we move pi over 2. It will be 3 over 4 pi. 3 over 4 pi, if you check the tangent, it will be negative, right? It will be negative because the sine is positive, but the cosine is negative. So what's happened with negative 1? Radius negative 1. So it should be at the other part, but it is the opposite, right? So it goes back to the r equal 1. So that's why on this part here, the theta is also a 3 over 4 pi. It's the negative parts of 1. Let me check here. So tangent 3 over 4 pi is negative 1. So, or you could imagine when pi, well, you could say it like this. This is negative 1, 3 over 4 pi, right? If we take the r theta coordinates. We could also make this 1 and then pi minus pi over 4. So I think maybe one suggestion from my perspective is, aside trying to, like after solving this, check the other angle. Maybe you can move 90 degree, and check the whether it's logics or not. It makes sense or not. Okay. Maybe just a reminder, tomorrow will be quiz, okay? Quiz. I prepared just 3 questions. three questions. We'll be taking the second part of the course tomorrow. Okay? So we will have a course first and then quiz. Okay. So please check the exercise, check the my answer key. If there's any problem with my key, you can discuss. Maybe you have some questions. All right. I would like to move to chapter 11. Okay, chapter 11. So chapter 11 is about the sequence, series, and power series. So we are going to look at sequence series. Perhaps some of you may have learned before, right? But now we are going to look on in calculus perspective, okay? And how to make the series relate with calculus, okay? Especially if you remember, the sequence can be like infinite sequence, infinite series, and some of it maybe we could conclude like, oh, the sequence is getting to some convergences, maybe some value, and that's where we are going to observe in calculus. Okay? Let me start with the introduction first. Okay, let's see this picture. It's the same as in your textbook. So there's a problem here. It's called the Zeno paradox. The Zeno paradox is stated that, imagine you are walking, okay, walking from this point here. Okay. You are walking, and then you want to approach, let's say, this wall. Okay. But the way you walk, you can only walk half by the total distance. So first, you try going half. Okay, so imagine maybe this is just 1 meter. So half meter. And then you get half, right? But the way you approach, you need to take half of it. So you go 1/4. And similarly, you go 1/8, you go 1/16, etc. The question is, can we see the man touching the wall?
No.
If you imagine in reality, probably not.
It's popular paradox. There is a solution.
Yes. It's a popular paradoxes. But here in calculus, because we use the limit concept and everything, we could like ignore some of the points, and we could say, well, we could take approximations. It's close to 1, which is 1, right? We take the limit concept of it. But that is one way to see. And the way we describe the distance, like half, 1/4, 1/8, 1/16, 1/32, and we could take that, okay, this is like a sequence. The pattern is 1/2 with power of n. Okay. And this has become a sequence. And the sequence, if we take the sum, maybe it's close to 1. It's close to 1, right? If we plus all of that, when n is getting infinity, and we take the limit as n approach infinity and so on, and maybe we could figure out that is 1. Okay. So this is an infinite sequence. So this is, we call the infinite sequence, or just sequence, or just a sequence. And we could write the sequence in a, usually we write with terms A1 like that, A2, A3, A4, and we could simply just write A, N. So we say A1 is the first term, A2 second term, and so on. Okay. We could denote this number here with some brackets like this, we could say this is a sequence. So whenever you see these symbols, which means that is a sequence. Or precisely maybe starting from some n, maybe n equal 1 until maybe infinity. So you could also describe which n you are going to start with. Okay. But the assumptions, the default settings, n is always equal 1, unless there will be some special on other n. So we could write the first one here, the Zeno paradoxes pattern. Maybe you could write in terms of like this, with a bracket. Or we could write with the name an is, okay. Okay, in a sequence, perhaps you are going to find the pattern itself. Okay. For example, you are given some list of numbers, and then you need to find how the formula for the pattern. Okay, for example, here, let me write this part here. If you are given, let me write with the finding the pattern or formula for general term. Example, you are given the sequence 3 over 4, oh, I forgot to charge the pencil. This is later on. I will write that. Okay. Okay, find a formula. When we are given these terms, 3 over 5, negative 4 over 25, 5 over 125, negative 6 over 625, 7, 3125. Now you will see that in the denominator we have 5 and then 25, 125, right? So this is the first term, second term, third term, and so on. And if we carefully see how the denominators is, I think it has a ratio of 5, so it's multiplied by 5, right? How about the numerator? It starts from 3, but it started with negative 4, and then 5, and then negative 6, and then 7. Okay, we take a break. We'll take a break. Okay. Okay, so the sequence. Okay, we continue. So we have an example here, and one of the typical example for a sequence is finding the formula for its general term. So if you look the denominator and the numerator, I think we can get something, okay? But the problem I think that arises here is there is a negative signs, okay? So it's positive, negative, positive, negative, positive, right? So perhaps we could write down first what's the original. So if we take out the negative signs, then we could immediately see that perhaps the ratio is on 5, right? So because it's multiplication of 5, so we could take with some n, right? We could take with some n. And the numerator, because it starts with 3 and then 4, 5, 6, 7 and increasing, it's just like n, and we could just plus 2 the n. So n plus 2. So we could check with n equal 1, 2, 3, 4, and I think it's matched with the numbers. Okay. And then we could take, to make the negative signs, we could take -1, let's say with power of n. If start with n, then it start with negative. So maybe we could plus 1 or minus 1. Let's maybe minus 1, because it will be with power of 0, which is positive.
Why is n plus 2?
To make it 3, 4, 5. N equal 1 plus 2, 3, 2 plus 2, 4, 3 plus 2, 5, right? Okay. And then we could combine these two. So this is for alternating sign. So we could write a n So alternating signs can be just -1 with power of n, or n minus 1, or n plus 1, depends on how we see the pattern. And some patterns, they don't have simple definitions. Like for example, the Fibonacci sequence, it has a its own rule, right? It has its own rule. It has like a recursive definition. Right here, a Fibonacci. You still remember what's Fibonacci sequence? Let me just write the number. Start with what? 1, right? And then 1. You start with these two numbers at the first term and the second term. And what will be the third term?
The summation of
Yeah, we plus, right? We sum the first and the second is 2. And then we plus 1 and 2, become 3. And then 5, and then 8, and then 13, and then so on. So we define, and then so assume the first term is 1, the second term is 1, and then the general formula. And we start with the 3. We start with n equal 3. we can have precisely fit. Go here. Think that. Let's move it to the right. Okay, now we are going to first, this is the, let me write the title, limit of a sequence. Like you imagine with the Zeno paradox that we have. But let me write another sequence. Let the sequence be n over n plus 1. We could write this starting from n equal 1. This is 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, and so on. Okay. Okay, and then let this sequence, let's put into a graph. Okay. A graph with n as an x-axis and an in y-axis. Before graph, we could put the n and the term in terms of this line numbers. Okay. So we start from, this is from n equal 1, which is half, okay. And then the second term, which is the 2/3, this is 2 over 3, right? And then 3 over 4, and then 4 over 5, okay. And you see, when we increase the n, it's going to have like this, a lot of points, right? We increase from A1, A2, there's a gap, and A2, A3, the gap is closer, and then to getting A4 is also getting closer, and then 5, 6, and then when we go by nearby 1, we have a lot of like closer and closer and closer, right? Yeah. Okay, perhaps it's not really clear what's happened here, but if we take the graph of the n and an, you can see that the dot is getting closer to some number, which is this is equal 1. Okay, if we take n more and more, getting closer to 1. So look at this at n equals 7 is 7 over 8, and imagine that when n is perhaps 99 over 100, it's almost like it's getting closer to 1, right? It's getting closer to 1. So we could say that in the sense of that n is getting larger. So let me write Sn becomes large. Or n is getting infinite. We could write or we could determine through the limit concept. And then if you remember the limit, then this is going to be equal 1, right? This is going to be 1, 1, and this will be going to be 0. Okay? Still, I hope you still remember the limit. Okay. Let me maybe take this. So this is 1. So in more general notations, we could take the limit of the sequence. This is equal some L. which means we could determine the some value. So we say that this limit is converges, or the sequence is converges. Or convergent. So we could write as an getting L and n getting infinite. The bottom one haven't yet. Maybe here. This is another converge sequence. Sometimes the sequence can be a start going up as you increase the n, and later it will go down and then get a consistent value. And some other terms, they will go up, down, but their amplitude is getting smaller. Their amplitude getting smaller, and they're getting to one consistent value. And because of this also can be considered as a converge sequence. Okay.
So we have equal in between the limit and
Oh, why I'm writing? Okay, thank you. Okay. So if there is a converged sequence, there will be diverged sequence, which means that there will be a sequence that is not going to have a finite value or consistent value. We are going to go and observe those sequence. Okay, the next one is going to be the precise definition. So let me write the definition first. So sequence AN has limit L, and we write first the first definitions like we did previously. So AN getting L and N is getting Sn getting larger. And this is true if for, so we are going to use some, how to say, like a smaller abstract concept that there will be a small gap we call the epsilon. Okay, that correspond with some integer n. So that n, this capital N, can be any number that relate with the epsilon, such that if the n is greater than the integer capital N, then this differences between the an and L, this is always less than epsilon. So epsilon, if you remember the calculus one, is a really abstract concept that we imagine that there were small spaces that we, like when we did the Zeno paradox, when we approached the wall, in real life we couldn't approach it, right? In real life we never approach it, but in a limit we have a sense that, okay, since it's a small gap, then we could ignore it. But how small that gap is, that is the epsilon. That is the epsilon. Okay. So we are going to say that between those small gaps, the differences between the an and L is always smaller than that gap. And if we want to take the, how to visualize the L, let's say we have the all the terms here, and let's say we are going to take this terms. Okay, so let's say L is going to be here. Okay, L is going to be here, and we have the epsilon as the distance between these two, and all the terms that is in this capital N is always in between these two distances. Okay. This is how this is going to be defined. Huh?
What is epsilon?
Yeah, epsilon is like a small gap that defines the differences between an and L. But the difference in an and L is always smaller than that. It is just as if we look at the limit, it's actually like we say, if we want to take like something equal 1, we could say 0.999999, right? Okay, it's something like that. Okay. Okay, and the second graph, you see, if we increase n, like usual, and let's say the L is our value that is consistent, the limit value. The epsilon is on here. Okay. And let's say the capital N is on this value here. Which means that the capital N here will be going to be in between these two lines, the L plus epsilon and L minus epsilon. So no matter how small epsilon will be, this two picture will be true for all n. So this is, every time we have, like in calculus 1, you have also the precise definition limit with the epsilon and the delta, right, if you remember. And now we also have the epsilon definition. In real life, it's not that applicable, but in mathematics, we need to define everything. Like how small it is. Like if you say the limit, oh, the limit is equal 1. But limit is not the real number, right? It's a approximation to some number that we need to define how small it is. The differences with the limit and the actual number that we need to define. That's the epsilon actually is. Okay. It's a little abstract, but we need to define that. We need to define that. Okay. Now this will be a picture. Okay, so if you look at the left and right picture, the first one, it goes like it can be random, it can be like it has a pattern, but the pattern we couldn't determine where it will be in a, is there any consistent value when we increase n? And I think they are not consistent. And we say this is the diverge. This is diverge. Because there is no precise or finite value or consistent value. The second picture, we go like up and up and up, and it seems that never end. So we say that as n increasing, the value for the an is also increasing. So both pictures, they have divergent conclusions. So they are diverge sequence. So sequence is divergent. This is a limit, or limit as n approaching infinity. The an is infinite. We can also that. And in precise definition, for the infinite limit, so these notations, it means for every positive number, let's say capital M, there is n such that if n greater than n, then an is, this is to show that whatever big number you have, like this m, the an is always bigger. So it's supposed to be defining that the limit is going to be infinite. And I think other analogy also apply when you have the negative part. for the infinite. This is also true for the negative. Okay. Now we could also describe s in a function of x. So if limit x approach infinity, f of x equal L, and f of n is the an itself, when n is integer, then we go back to the definitions, the sequence with limit. That is true. So we could describe the an in the terms of functions. I think this should be very intuitive, right? And since we describe most, like all the sequence with limit, because we have the infinite sequence, then we are going to apply all the limit law. So if we have the sequence A and sequence B that they both are convergent, then all the limit law that you have learned before in limit, they are all applicable. They are all applicable, okay? So we can take the plus subtractions. We have a multiplication with a constant. We multiply the inside the limit, and we can separate them. And we can define, and we need to make sure that it's not equal 0 for the limit for the denominator. Okay. Okay. Okay, I think this can be skipped here. Then because we discuss on limit in a sequence, if we imagine if we have three different sequence, A, the black dots, okay, and then B, the red dots, okay, and then C, the blue dots, okay. And if you remember, because we learned limit before, and we learned that If B is in between of A and C, and we could have the squeeze theorem, the same squeeze theorem with limit. Okay? We can also apply in sequence. So if the AN is equal with B, and B is less equal with C, and for N is greater N0, which means the next N is greater equal with the previous terms, and limit is equal with the limit with the C, which is L, then limit Bn is equal with L. The same, very similar with the calculus 1 counterpart. Okay, this is the squeeze theorem. Theorem for sequence. Well, let me write the two simple theorem below here. The first one is the power law. P is the power. But I think this is also the same with the limit that we have learned. And another simple theorem that useful is when you have the absolute value of the AN. If this limit is 0, then limit of the sequence also 0. And by the way, the feedback, like in the Mentimeter, why I think our last 2 or last 3 feedbacks have some trouble. I think because now they are really sensitive in their server. So whenever you open, if you take your phone and maybe either not close, maybe just go out for a while from the apps or from the browser, it consider as idle or disengaged from the connections. So that's why it's counted like everyone was voted. So perhaps we could make sure it's always on your phone. Will it still happen? Maybe I need also to complain on the I just complained to the server to the Mentimeter. Well, let's try if they are good enough. If no, then perhaps I need to maybe make another platform, looking for another platform. Okay, I think I will stop until here, and we are going to have a feedback. Okay. I think I will just go open through my iPad. Okay, and hopefully it will be clear and for you not to be disengaged from the browser. But if it still happens, then I need to complain more. Okay. This is to check whether you are ready for tomorrow quiz. I think 21 students around, right? I think supposed to be, right? Yeah. Okay. Just a small question. How are you feeling today? Describe your feelings today. Anything you can write? Maybe sleepy, right? Early morning class is sleepy. Too bad. Oh. Hurt? Why hurt? I love Travis. Okay. Oh, hungry. So you haven't taken breakfast? Tired? Okay. Okay. Okay, I think we not ready. Okay. Depressed. Wow. But anytime you have like any problems, not only the calculus, like if you need something else, maybe to help you more, maybe to get rid of your depression, or I think if you make the word depression, it's already like not really a good word for now, right? For the mental issues. Okay. But you could talk to me if you like. So you can talk to me not only for academic, like for anything else. If you want to talk, you can come by, or you can just write an email. Oh, 30 play ready. Okay. Okay, let's start. 3, 2, 1. I hope the time is sufficient. Yeah, too small. It's around 5 minutes. R is 1 over theta. Theta is equal pi. It's asking slope of the tangent line. Okay, it's okay, it's okay. Yeah. Okay, okay.
this formula.
Maybe
Just use the formula.
1/3.
I'm checking.
Yeah, 1/3.
I'm not checking. I think I did it. Forget again. You can always press the pin. Huh? You can always choose pin. Whatever.
Careful, careful. Remember, the slope means that you are going to compute the dy of dx, right? You could approach with just a normal parametric, or you could approach with a polar. The same result. And remember, the x is r cosine theta, and y is r sin theta. Okay. Oh, okay, same thing. I think, yeah. Okay, the next question. Who is this? Go down. Okay. Okay, the second question. We have the second question. Okay. 3, 2, 1. Let's start. Okay. You need to write. Uh-huh. It's not often. Remember the length of the curve. So in parametric, you have the x dt, right? And dy dt. And you have ab. Yeah. And remember what will be if you have the polar. Okay. You can open your notes. I think I already write that for you. What will be? Or if you want, and if you forget, for example, in exam, you could start from this and then relate with this x and y, and then find the polar partial. Oh, precedence. Yes. And careful in your calculation. most of the time you will have a square. You have the quadratic equation that you can find the quadratic form, and you can cancel with the square root. Okay. Most of the time that will works. Maybe some maybe something. We need to find the integrations. Integrate. What's the fifth logic? Theta is from 0 to 2 pi. I mean, it's not mentioned, but suppose that the quotient, then you need to assume it's a first of full circle. Are you sure? There's something missing? The square root of 2 should be cancelled. Just multiply this with another one.
Oh.
Should be r squared plus dr d theta squared, and then take the square root, right? And you will have a quadratic equation. Solve a little bit, some algebra, and then make the quadratic form, cancel the square root, right? Confused on what the theta, imagine like a circle. So if there is no mentioning about the theta, you can imagine from 0 to 2 pi. Yes. Yeah, almost. But this cosine you can try to find the. Can you find the square? Okay, this some students got correct. Okay. Okay, two students, only two students got correct. Okay. Okay, can you listen? I think you're okay. Okay. So lastly, the student ID and feedbacks if you have. And that will be the end.